Welcome to the Earth Science Division's Distinguished Scientist Seminar Series. This seminar series is sponsored by the Office of ESD's Director, Don DiPaolo. And the series is a monthly seminar. It features eminent individuals in Earth Sciences area whose research is outstanding, interdisciplinary, and of broad interest to the strategic initiatives in the relevant areas. It is my honor today to introduce the speaker, Professor Peter Cook. Peter is a principal research scientist with the CSIRO and also professor at Flinders University in Australia. He got his PhD in Earth Sciences from Flinders University in 1992. And his research areas include groundwater hydrology, eco-hydrology, isotope hydrology, and unsaturated flow, with focuses on the use of environmental tracers and on the interaction of tracers and hydraulic methods. And he's a co-author of books on the environmental tracers and eco-hydrology. He's currently the Deputy Director of the National Center for Groundwater Research and Training for Australia, and also the leader of its surface water-groundwater interaction program. And Peter has received many awards in his career, and his 2009 National Groundwater Association Darcy Lecture. With that, Peter.
Thanks very much. The last time I think I was in the States, I was in the middle of the Darcy lecture, and I was talking there about some work we've been doing at trying to understand groundwater flow and transport in fractured rocks. But I've given that talk as many times as I'd care to give it. So what I want to talk about today is some work that we started doing about 5 or 10 years ago, but it's really become the focus of our research within the last year or two, looking at regional scale groundwater surface water interaction. This is a sort of diagram that you'll find in many textbooks. It just shows the distribution of water on the Earth's surface. What's important, though, if we start to ask questions about sustainability, is not so much the volumes of the different reservoirs. What starts to become important is the replenishment rates or the recharge rates of the different reservoirs that figures like this give no information at all about. I wasn't able to get sort of continental scale US data on replenishment of or recharge rates of reservoirs, and I'm not sure whether it exists. This is some Australian data, and it shows the mean annual stream flow, but there's a figure for the divertible surface water yield. So the amount of surface water that's theoretically capturable of about 26,000 gigalitres per year. And I think, coincidentally, a very similar figure for the sustainable groundwater yield. And I don't want to go into how these figures are put together, and no doubt they're extremely dodgy. The question, though, is what's the intersection between those two reservoirs? Because the total available yield depends on the intersection of the two reservoirs. If there's no intersection that's drawn there, then the total available yield, of course, is 52,000 gigalitres per year. But if the intersection between these two reservoirs is 10%, the yield drops down to 49,000, and so on. So it's very important to understand the intersection and the exchange of water between surface water and groundwater if we want to understand what the total available groundwater resource or total available water resource is. This is just a pretty basic classification that's probably familiar to a lot of you. When we talk about groundwater surface water exchange, it's sort of regional levels, water resource levels. There's a fundamental classification that's been used between gaining and losing streams. Gaining stream where the groundwater is discharging into the river, and a losing stream where the river is feeding the underground aquifers. And this is just a very simple schematic from a report of Winters looking at, so here on the top, initially a gaining stream where the groundwater is flowing into the surface water. In the second diagram, there's a bore here some distance from the stream, and that bore is intercepting groundwater that would have discharged to the stream. It's not at this time actually pumping stream water. The bottom diagram C shows a stream where it's either pumping at a greater rate perhaps, or it's been pumping for a longer period of time, and the stream is now actually capturing stream water. So it's turned what was a gaining stream into what's now a losing stream. And this is a pretty fundamental schematic cartoon for the impact of groundwater pumping near streams on surface water resources. This is another pretty famous diagram that some of you may have seen before. Marios Sophocleous has used it on several occasions. It shows the distribution of perennial streams in Kansas in 1961 and then in 1994. And the area shaded in the light green here is the area underlain by the Ogallala Aquifer. And so the diagram shows that in areas underlain by this widely utilised aquifer, most of the perennial streams are no longer perennial. Well, or no longer were, it's almost 20 years ago now. I haven't seen a more recent update. This is the Murray River in Australia, which is Australia's largest river system. This is the mouth of the Murray River, and the Murray River now in most years no longer reaches the sea. And there's continually dredging in the mouth of the river actually to keep the mouth open. So there can be some exchange of water between the fresh water and the seawater. This is further upstream of the Murray River, and about 20 years ago there was concern about use from the Murray, and so there was a limit, a cap put on further pumping from the river. Around about 20 years ago, perhaps more, no more pumping could take place directly from the river. But they didn't cap groundwater pumping. So you put a bore 5 metres from the river and you pump as much as you like. We've now addressed that, and there's also caps on groundwater use, but it just shows some of the difficulties that you get when you manage groundwater and surface water separately. And there's been a number of figures have been produced for the impact of groundwater pumping on streamflow. This is a slow process because the impact of groundwater pumping on streamflow can take many years or decades to be seen at the stream. And so it's predicted that there's a 186 gigalitre per year loss of streamflow by groundwater pumping, which will increase by up to 700 gigalitres per year in the next 30 or 40 years or so. And of course, one of the problems is the loss of streamflow also occurs during low flow base flow conditions when it's most important for ecological purposes. The question arises though, so it's clear while we shouldn't manage groundwater and surface water. Separately, the question arises about how should we best manage them. I've seen some streams where they are fully aware of the issue, and so they just, to avoid that picture I showed previously, they say, okay, any groundwater bores within 300 metres of the stream will be considered surface water takes to try to avoid the issue of people putting bores right next to streams. That's not really conjunctive management. That's really just moving the boundary between what we call a stream and what we call the groundwater. We know that managing, just working out the size of the whole bucket is not the best way to go either, because groundwater has a reservoir value that we can take advantage of. We could pump more water from the groundwater during a drought when we can't pump more water from stream flow. So there's some advantage in pumping groundwater over stream flow, at least in times of low water supply. It's clear we don't really know. I haven't seen a good example of conjunctive groundwater surface water pumping, and I don't think we really know how to best manage them together, short of using a very sophisticated coupled model. It is clear, though, that one of the first steps is to know what the exchange flux is. So what I want to do this morning is firstly talk a little bit about the processes of surface water-groundwater interaction. I then want to discuss what the different methods that are available for quantifying the flows of water from groundwater to surface water, and then move on to talk about some of the techniques that we've been using for the last few years, trying to use water chemistry, and particularly the radioactive gas radon, to quantify surface water-groundwater exchange. Just before I go further, a little aside, that something called disconnected rivers have become quite the flavour in Australia recently. A disconnected river, and the terminology is perhaps unfortunate, but a disconnected river is a losing stream where there's an unsaturated zone that separates the stream water from the groundwater. the water table drops to such an extent that the saturated connection breaks, and we have the water table is some distance beneath the stream. What happens as you drop the water table, the flux starting from a situation here, the infiltration flux to the groundwater increases, but then when you get in a disconnected state, it levels off, and you just have gravity drainage. The water table dropping further no longer affects the infiltration flux. So it's been very tempting in Australia to classify streams as disconnected streams with the assumption that, oh, well, then we don't have to worry about conjunctive management because groundwater pumping no longer affects stream flow in a disconnected stream. That's unfortunate because although it's true that lowering the water table further in a disconnected stream doesn't affect the infiltration rate, changes in river width, changes in river depth will still affect the infiltration rate from a stream to the groundwater. So although for a disconnected stream, groundwater management may not impact stream flow management will still impact groundwater. And so we still need to manage them conjunctively. I want to talk a little bit about scales of groundwater surface water exchange. In fact, a lot of the work that's been done in the area of groundwater surface water interaction within the last 10 years or so, much of it in Europe and North America, has been focused on the small scale exchange of water between the water flowing in a stream and the water immediately beneath the stream bed, on scales of millimetres or centimetres up to about a metre or so. This so-called hyporeic exchange. It's not what I want to directly talk about, but really a lot of the work has been in this area. It's very important exchange for a whole bunch of ecological and geochemical processes. I want to focus at sort of the regional scale, the gaining and losing streams, how we can quantify exchange fluxes at the scales that regional water managers care about. Scales of tens to hundreds of kilometres or more. There's some sort of in-between scales there that we also need to be aware of, and I'll discuss a little bit. Sort of bank storage changes. As stream levels rise and fall, water moves in and out of the stream bed. The stream goes up, water moves into the groundwater. As the stream falls, groundwater returns to the stream. So there's some in-between scales, and these operate on scales of metres to tens of metres. Both of these processes, though, are gross fluxes. They're not net fluxes. Okay, there's no hyporeic exchange doesn't cause a net flow from groundwater to surface water. It's just moving in and out. And bank storage as well is sort of an in and out process that are superimposed on this more regional gaining losing situation. This is the Cockburn River that I'll be talking about a little bit more later on. It's in southeastern Australia, and it's one of the headwater streams to the Murray River. The Cockburn's one of the few streams that I'm aware of where we've estimated both the regional groundwater inflow rate and the hyporeic exchange rate on the same stream. People that do hyporeic exchange work and people that do sort of regional groundwater work are a bit like surface water and groundwater people. They tend not to talk to each other and they do their work in isolation. This is one of the few streams where we've done both. And what I just want to point out is that the hyporeic exchange, which is not a net flux, it's just water moving in and out, is around almost an order of magnitude greater than the net groundwater flow to the stream. And this has pretty important implications if you're trying to estimate this number, because there's a whole lot of in out, and we want to measure the very small net flux. And so this really complicates the measurement. Few words about spatial variability. There's been quite a lot of studies on spatial variability of groundwater surface water fluxes in the last few years. This is an older report of Winters, just showing, so this is the stream elevation here in blue over quite a small distance, and just pointing out how groundwater, where you get these break of slopes in the stream bed, groundwater moves into the, or stream water moves into the groundwater here and comes out here. So there's water moving in and out of the stream bed associated with these changes in surface topography as the gradients change. There's been a bit of theoretical work showing in a homogeneous system, you would expect groundwater discharge to a stream or to a lake to occur at the shore, at the bank. This is shown diagrammatically in this diagram from winter, but also shown sort of some calculations modelling by Genero, showing that seepage decreases exponentially as you go offshore. So in a homogeneous system, it's actually all happening at the bank. More recent, some really nice work by Dave Genero and Kennedy and others that have looked at spatial variability of groundwater discharge. We've got a scale, there's a scale, 50 metres. So this is within a stream. Quite high spatial variability of fluxes. They also found that it often doesn't occur at the shore, at the stream bank, because the sediments tend to be coarser grained near the middle of the stream, and so that sort of works in the opposite direction to this process here for a homogeneous stream. But the point is, quite high spatial variability of fluxes over reasonably small spatial scales. I want to talk a little bit now about how we might characterise groundwater surface water interaction, how people have been trying to quantify that flux, and the applicability of those methods for sort of regional scale approaches. Most obvious, as a groundwater hydrologist, of course, the most obvious is to use Darcy's law and to look at the gradient between a bore adjacent to a stream and the stream. Now, it's interesting here, not only have surface water and groundwater been managed separately for the last 100 years or so, and certainly in Australia, they were usually in different government departments that were responsible for managing those two resources, they devised completely independent monitoring networks. And so I'd be surprised if it's different here, but we have very extensive surface water gauging station networks, and similarly very extensive groundwater monitoring networks. But has anyone thought about putting groundwater bores next to surface water gauging stations to measure the exchange flux? There's actually very limited data where we're able to do this. And for a long time I thought, well, this is what we need to do. We need to make sure we've got groundwater bores near gauging stations to look at the exchange flux, look at the tendency for exchange. It turns out that would give you a very, very local measurement. Not only is there a problem, as we would all know, from measuring hydraulic conductivity to quantify the flux accurately, and the hydraulic conductivity of stream bed sediments is particularly variable. Work of Calver and others have shown that. But depending on the distance your bore is from the stream, you're probably only measuring, if your distance is 50 metres from the stream, you're probably only getting information on the exchange flux over a distance along the stream of around about 50 metres as well. So it actually proved to be quite a local flux. And while important for understanding processes, it's perhaps not going to be helpful at regional scales. The technique that's been used perhaps most widely since perhaps the 70s, work by Lee, is seepage meters. Seepage meters are essentially upside down buckets pushed into the stream floor, and they're attached to a bag here, a reservoir, a plastic bag, that groundwater that enters the chamber fills the bag, and so at regular intervals the bag is disconnected and weighed, and from changes in volume of the bag we can calculate how much water is entering the stream or leaving the stream. There's been some really nice process studies using seepage meters, most of it actually looking at submarine groundwater discharge. These have become a very widely used tool for looking at groundwater discharge to the ocean. This is just some data that I took from a recent paper, and you can see this is the... And so the seepage meters have been brought into the 21st century, and they've got heat pulse and electromagnetic means for measuring flow. You don't have to actually detach a bag anymore. And so we can get records of discharge over time, and in this paper it was linked to variations in water level and rainfall and wind speed. But you can do some really nice process study looking at how the fluxes vary over time and what sort of factors control that. Of course, the issue is that you're measuring the flux over an area of about this big. Perhaps a little bit less of an issue in submarine groundwater discharge studies because the permeability of seafloor sediments may be less than the variability of the permeability of stream sediments, but certainly it's a very, very local measurement. And there's really nice, really important for process understanding, but really hard to extrapolate to catchment scale exchanges. One of the other methods that, if you sort of search on surface water groundwater exchange in the last 10 years, you'll find a plethora of papers using temperature. And the traditional approach was to put thermistors beneath the stream bed. So you put a thermistor within the stream, you put some within the stream bed, and you look at diurnal variations of temperature. This is just shown here. We'll look at the bottom one first. So the blue line is the diurnal variation in temperature within the stream, and the black line is within the thermistor buried within the sediments. And so this diurnal variation, for a losing stream, if the waters are moving down through the stream bed, you see a attenuation, but also a phase lag in that diurnal variation. It takes a while for the highest and lowest temperature to move down to the sediments. And from that phase lag, you can calculate velocity. And people have been using this to look at velocities of surface water infiltration to streams. The difficulty with that, of course, is again, it's a very local study and relies on thermistors within the stream bed. There's been some quite nice work lately, Steve Lowhide and others have been doing, trying to estimate exchange rates from stream temperatures alone. If you don't need to actually bury something within the stream bed, then the technique is much more suitable for extrapolation. We can measure, this is actually stream temperatures measured from a helicopter. We can use remote sensing. Actually would lend itself to some regional extrapolation. So in this case, the theory is where groundwater, because groundwater is a reasonably constant temperature, where groundwater is entering the stream, the diurnal variation in stream temperature is compressed, such as in this area here. So this was done over about 1.6 kilometres. In here, stream temperature measured at different times is relatively constant compared to over here anyway. And so this is an area of groundwater inflow where groundwater is leaving the stream or there's no groundwater, where surface water is leaving the stream or where there's no groundwater inflow. The variation in temperature would be more similar to the variation in the atmosphere. So you can calculate that at a qualitative level that there's more groundwater inflow here than here, but also Steve Loho did a full thermal temperature balance of the stream and used that to try and quantify the groundwater inflows. And so this is actually work that's potential, very early days, and I'd be interested to see how the errors propagate through this sort of analysis, but at least it lends itself to quite large regional extrapolation, although to date it hasn't been done on scales of more than a kilometre or so. The other sort of obvious method that comes to mind for measuring groundwater surface water exchanges is by doing flow gaugings. This is a guy measuring flow in a stream, doing flow gaugings at different points down the stream, and essentially looking at the difference between the gaugings at different points. And if we can make corrections for evaporation or any other processes that affect the surface flow, we can calculate the net groundwater inflow or surface water outflow. That's just some data where we did a large number of flow gaugings on a stream over about 70 or 80 kilometres, and you can see in this case some very significant groundwater inflows due to spring discharge, but it's a means for potentially calculating the inflow or outflow rate from the stream. And that's just the water balance equations. I won't go into that. What we can do, well, so I will just very quickly. So, you know, the groundwater inflow is the difference between the flow measured here and the flow measured at this point here in this stream. What we can then do, though, is look at the solute balance alongside the water balance. And so as well as measuring the flow rate here, we measure the concentration. We measure the flow rate and concentration here. And we can solve the flow equation and the solute mass equation. The mass is just the product of the flow and the concentration simultaneously, and calculate the groundwater inflow rate in a mass balance approach. If we measure the concentration also in the stream, and we measure the concentration in the groundwater, which is CG. And so we've been using, and a number of people have been using that sort of approach to estimate groundwater exchange to streams for a number of years now. This is the Cockburn River again, and this just shows the electrical conductivity microsiemens per centimetre versus distance. A couple of dramatic changes where tributaries enter the river, but a lot down here you can see there's no more tributaries and the electrical conductivity increases quite steadily. If we know what the concentration of the groundwater is, we can calculate what the groundwater inflow is from that change in electrical conductivity. Other method that I just want to mention briefly, and I'll come back to a little bit later, is for again, since probably the 1960s, people have been doing hydrograph separation using tracers. And this essentially involves measuring at a point along the river at a gauging station, measuring flow over time, and also measuring concentration of a tracer over time. So in this case, this is the flow rate of the stream, total runoff. This is the concentrations of silica measured throughout that rainfall event, throughout that flow event. And from the changes in the concentration, in this case of silica, they would determine how much of this flow event was groundwater and how much of that flow event was surface runoff. So the assumption here is that silica in runoff in rainfall is essentially zero, and all the silica is out of the groundwater. And since the silica concentration only dropped by about 10%, then there can only be a 10% contribution of surface runoff during this flow event. And so on that basis, the authors calculated this is the groundwater contribution to flow within that upstream area. This is actually a technique that's become quite controversial in recent years. And there's been a large number of papers basically saying, well, something's wrong here. If you look at that last diagram, it indicated that 95% of that flow event in the stream was groundwater, and yet we know that groundwater doesn't move that fast. And that's essentially what these papers have been saying. Something's wrong. Groundwater does not respond to a rainfall event in hours. And there seems to be a contradiction there. And I want to come back to that a little bit. If you look at the measurement techniques that I've described, and we can argue about exactly where those bars start and end, the point I want to make is that most of them work at pretty small scales. And while temperature has some potential, I think, some good potential to work at regional scales, if we can understand the thermal balance of streams properly, what I want to focus on, the work that we've been pursuing, the work that we've been doing is driven by water management issues. Regional scale water management, where we need very large scale estimates of surface water exchange. So the techniques that we've been using and what I want to focus on from now on is looking at stream chemistry and trying to quantify groundwater surface water interactions by stream chemistry, which I still think has the best potential to be useful at regional scales. Because the chemistry of the stream at a point gives you information about what is happening in the entire upcatchment area. We still need to disentangle what's happening in that upcatchment area and how it arrived at that concentration, but whereas the other methods tend to be measuring more local processes. So I want to talk about what we've done using chemistry. And I'll just go back to water and solute mass equations that I put up. This is essentially the principle. We measure concentration and flow at different points in the stream. We need to know the groundwater end member, and that's the thing that's critical. If we do that, we can quantify groundwater inflow rates. So if we're doing that, we measure the concentration. We measure the concentration of what? In terms of choosing the choice of what we measure, well, we clearly want to use something that's easy and cheap to measure, or that's preferable. We want to use a tracer that behaves conservatively, or at very least, the non-conservative behaviour is reasonably predictable. If it must react, let's at least have it so that we can actually predict how it's going to react. But conservative is ideal. You want a high contrast in concentration between the groundwater and the surface water for it to be sensitive. If the groundwater and surface water have the same concentration, it's no use at all. So we need a high contrast in concentration, and we really want a groundwater end member that's as constant as is possible. One of the traces that we've been working on for about the last 10 years or so is radon-222. Now, radon is a radioactive gas. It's produced at the bottom end of the uranium-238 decay chain. It has a half-life of 3.8 days. It's a gas, but it dissolves in water, the same way that oxygen dissolves in water. And it's produced only in the subsurface. The radon concentration of the atmosphere is essentially zero for our purposes. And so if you have groundwater discharging to a stream, it will bring radon with it. If that groundwater then sits in the stream or in the lake, sits in that lake for a week, the radon will be gone. So it's an indication of quite recent groundwater discharge. I think I've said most of that. It's lost by radioactive decay. Because it's a gas, it's also lost by gas exchange to the atmosphere. Okay? It just volatilizes. And that's actually a more important process than decay. It's a faster process than decay. Because it's continually lost, that actually maintains the high contrast between groundwater and surface water. So the fact that it's lost is actually a plus. Whereas if you're measuring a solute, if there's a lot of groundwater discharging to the stream, if you're measuring a solute like chloride, eventually that stream will have the same chloride concentration as the groundwater. So it won't be useful anymore further downstream. Doesn't happen with radon because it's continually being lost. So it maintains that high contrast. This is one of the earlier studies. This, I think, was in South America, work of Ellen's. So this is moving downstream in this direction. Radon concentrations, and you can see the dotted line is the background concentration at that time. So essentially no radon here. Big peak in radon as groundwater enters the stream. Then it's lost. Some more comes in, and then it's lost again below that. So indicating very clearly the points where groundwater is coming in. This was over about 8 kilometres. So what we've done, I put up that water and solute mass balance before. I want to complicate that a little bit more now. If we've got a conservative tracer like chloride, I've just written those same equations in continuous notation, okay? So for flow, change in flow with distance is the inflow minus evaporation. This is a stream that's gaining water. And we can write a mass equation as well. The change in mass is just the inflow rate times the inflow concentration. Evaporation doesn't change the mass. And we can solve those simultaneously to get the change in concentration with distance as a function of two terms, a groundwater inflow term and evaporation term. Radon's a bit more complicated because there's some more things happening. Okay, so we've now got those same two terms, a groundwater inflow term, an evaporation term, a gas exchange term. Concentration decreases because of volatilization. And we've got a radioactive decay term. We get a handle on the gas exchange term by injecting, in some cases, by injecting another gas into the stream and watching how that disappears. That's what we've done to get a handle on that term. This radioactive decay term is easy. It's perfectly known, the decay rate. Where hyporeic exchange, I talked about hyporeic exchange before. I've become interested in hyporeic exchange because it's a nuisance to me. It gets in the way of the fluxes that I want to measure, and it also contributes radon to the stream. And so we've got a hyporeic exchange term here. As water moves into the hyporeic zone, it can pick up radon from the hyporeic zone. And then it comes back to the stream and it's got that extra radon with it. It's often small, but it's another term we put in here to be complete. Well, relatively complete, I guess. Radon is actually cheap. I can measure radon in the lab for cheaper than I can do ion chemistry. It is very, very cheap and easy to measure. This is just collecting a sample. We just pump so that we're getting it from below the surface to minimise water that's degassed. Fill a 1.25 litre soft drink bottle with the brand blocked out there. They're the best bottles for sampling dissolved gases because they're very, very high density plastic. If they weren't, your Coke could go flat, right? Very, very good for sampling dissolved gases. very high density plastic. We just sample in there. We then add a little bit of mineral oil that the radon gas partitions into, extract that, just squeeze the bottle, extract that mineral oil, it goes straight into a counter, we have a number within a couple of days. And I can get numbers for about $60. So it is actually very, very cheap and easy to measure. Not a very good slide, but I just mentioned that we did some injection with other gases to try and measure the exchange rate, the volatilization rate. So here is my little tank of SF6, 600 mils of SF6 with a regulator attached to 25 metres of small diameter plastic tubing, silicon tubing. And the gas just diffuses out of that over days. Throw that in the stream, leave it there for 2 days, go and measure SF6 downstream. And we've also done some measurements of the production of the sediments by taking some sediments from the stream, putting them in a little brass container, sealing it off, and letting the radon be produced by those sediments. We then measure that radon concentration. So we can get a measure of the radon production in the stream. So this is the data. This is back on this is the Cockburn River again that I showed you and talked a little bit about before. So this is the radon concentrations I measured. This is now over a distance of about 33 kilometres. We've taken about a sample every kilometre. That took us about 2 days. And you can see relatively low radon concentrations here, large spike in radon in this zone here. Decrease below that, but it doesn't decrease to zero, indicating there's still some groundwater inflow in this area here. This is the electrical conductivity that I showed you before. There are a couple of tributaries here, and then that increase in EC. This is the SF6 data. So I threw these diffusers in 2 locations, one up here and one up here, and then measured the concentration downstream. It's on a log scale, so it plots linearly on a log scale, which is consistent with the exponential decrease in concentration. And these are some river gaugings we made at a number of different points along the river. And we can fit that using that model, solving those equations, and calculate the inflow rate, the groundwater inflow rate to the stream, also the outflow rate, which is really obtained not so much from the chemistry, but by fitting the chemistry together with river flow data. EC data is not quite fit perfectly. Really, I just got the tributary wrong. And so the shape's good, but it's a little bit offset because the tributary concentration perhaps wasn't what we measured it, thought it was. But reasonably good fit for the data, and we can calculate inflow rates and outflow rates. What we wanted to do then, though, is have a little bit of a think about uncertainty and say, okay, we can calculate inflow rates with this method. How accurate is it? What if you'd just done flow gaugings? Wouldn't that be good enough? Why go and measure all this chemistry as well? And what was the benefit by, so if we could have just done flow gauging, what was the benefit added by first also measuring electrical conductivity? You're doing a flow gauging, you're there for half an hour, put an EC meter in, not hard to do. What benefit did it give us? Also measuring chloride, also measuring radon, also measuring SF6. So we asked ourselves, each progressive measurement, how much did that improve our estimate of groundwater inflow? Just briefly, we did this using PEST, which is a parameter estimation optimization code that's freely available, I think. And we had to ascribe an error to our data to use that. We said, what is the error of each of our flow gaugings? We said it's about 10%. We said there's a 5% error in these measurements. Analytical error is much, much less than that. But there's other sampling errors and errors to do with the variation across the stream. So that's why we've used bigger numbers. So we ascribe an error. We ascribe that the error in end-member concentrations was based on the variations we observed in the field by sampling the groundwater. So I want to show you first the results for the Logan River, which is another river, sort of similar size to the Cockburn that I've been talking about in Eastern Australia. So if we just fit the flow data, so these are the points of flow and the error bars, then we calculate that's the inflow and outflow just based on the changes in flow we measure. We then add EC data and fit the whole model again. And we now get quite a different picture of groundwater inflow. We actually get no areas where there's loss in this case. It's all inflow, around about 0.2 cubic metres per day per metre. We add chloride and fit the model again, and you see the inflow rate changes. We can add radon, refit all of the data, and we get a slightly different, so the black one in each case is the most recent estimate. And you can see, if we add more data, we get a slightly different picture. If we also do our injected tracer, we again get a slightly different picture. What we've then looked at is what the total inflow is over that whole section of stream that we looked at. And these are the results. If we just did flow, we have some inflow rates and some outflow rates. Over the whole distance, we get an inflow rate of about, whatever that is, 0.02 cubic metres per second. When we added the EC data, we got this value, and so we got some changes in what the value of inflow rate is. But most interesting, they're the error bars when we use PES to calculate the error. And so you can see they're actually all consistent within the error. And that when we just had flow data, the error was actually this big. As we progressively add data, the error decreases. When we added EC, it decreased a little bit, chloride a little bit more, radon it decreased quite a lot in this case. And when we did the gas exchange experiment, the error increased a little bit further. This shows that data again. So this is just the inflow error for the Logan that I just showed you, but also two other sites where we did it, where we've looked at how that error changed as we added data. And the way I think we need to start using this sort of data is to say, well, you want to know what the exchange rate is. How accurately do you need to know that? And we can start to say, okay, if you need to know it with this error, then you need to use these sort of approaches to get that sort of accuracy. If you only need to know it really crudely, then maybe just the error you get with just flow data would be sufficient. Just in the last few minutes, I want to talk a little bit about one of the most critical things for using tracer methods like this, which is definition of end-members. And we define those end-members by measuring the concentration of the tracer in the groundwater in available bores. When we're using radon, radon has a half-life of 3.8 days. So the concentration in groundwater discharge is determined by the geology within about the last 10 days of travel, which is probably distances of metres to tens of metres. So there's a caution in using a bore a kilometre away to tell you the end member. There's a danger there. We'd be better off sampling in just sort of dry points right near the stream to get that end member. But also the stability of that end member with time is something that we've started to worry about. Processes such as bank storage could mean that the concentration of water entering the stream could change considerably over time. And I think this is one of the reasons of this apparent confusion or paradox with the hydrograph separation method with chemistry, is that during these runoff events, the chemistry of water entering the stream could change tremendously. And to assume it's a constant, I think can explain some of these problems people are getting with base flow separation. We've done a little bit of modelling on that I just want to mention briefly. So this is just our cross-section through a stream. This is the aquifer, the stream sitting here. And we've just looked at what happens as the water level in the stream goes up and down through a storm event. So just with a sine wave variation in head in our boundary here, and looked at what happens. So we've assigned different concentrations to reflect the river water and the groundwater. So the river, the height of the stream goes up and down. Water moves into the stream, water moves into the groundwater, which is a negative flux here. And then once the wave passes, it comes back out, and then you go back to a sort of a steady groundwater inflow. So we had a steady groundwater inflow that we superimposed this riverhead variation on. And the bottom diagram just shows the volume of bank storage. Water moves in, we get more and more bank storage, and then it all goes out, and we're back to where we started off. This is the chemistry of water during that process. This is actually the chemistry of water at the height of that bank storage. So 1's a groundwater and 0 was river water. We just tagged it in that way. And so you can see that the river water moves into the aquifer, in this case about 2 or 3 metres. When that flood wave disappears though, the water that discharges is not going to be a groundwater, it's going to have this water that's a mixture of groundwater and surface water is going to come out first. That's shown by this diagram, okay? So this is the water flux. Water moves in, water moves out. These are the results of the model. This is the concentration of water discharging to the river, which, if you like, is the fraction that's groundwater, because I've just tagged them with 0s and 1s. And so what it says is that that return flow is actually nearly all surface water, and there's just a little bit of groundwater coming out with it. This is just another simulation where we put a lot of, every 20 days we put another wave down the river to simulate continual sort of rainfall events and flow events on the stream. These are the fluxes that result, water moving in and out of the bank, into the bank, out of the bank. And this is the concentration of water that's discharging to the river. Interestingly, and it will depend on the frequency of these flow events, the concentration of water discharging to the river is never anything like what the concentration of groundwater is. There is always a mixture of groundwater and surface water discharging to the river. This plateaus at a concentration of maximum about 0.6. So when we're doing these end-member calculations, measuring the groundwater to tell us the concentration discharging to the river could be very dangerous. We will overestimate the concentration. Not as bad with radon. So the red curve now is if you do these same calculations for radon, because when bank storage goes into the stream, it picks up the radon. The radon is regenerated. It doesn't continue to bear that surface water signal. So it's not as bad, but we still need to be aware of, and it's something with all of these chemical separation methods, the stability of the end member is something that we haven't probably focused on enough. So just to conclude, conjunctive surface water management requires that we estimate surface water groundwater exchange, and the scales that managers need are in the order of hundreds of kilometres we need these information for. It's still something that we can't really do very well for them. I think chemical mass balance probably has the best potential for getting those sort of numbers over the right sort of scales. But I will say that the temperature is also promising, but perhaps a little further away. But temperature is interesting because you can measure it at all sorts of scales and even from satellite. So I think there's a lot of potential with temperature as well as chemistry. Knowing the groundwater end members is critical. It's something that we haven't focused on enough in the past, and I think that the assumption that they're constant in time is the problem with these chemical base flow separation methods that I mentioned have been so controversial in the last few years. Thank you very much.
Yeah, we have time for some questions. Yeah.
I have questions just on some of the details. The overall message is very impressive. Thank you. But in one of the first slides that you showed, you talked about a disconnected stream. And I have difficulty understanding how you can have a disconnected stream if you have perennial flow. And I would seem that you only could have a disconnected stream if the flow is intermittent.
No, you can have a disconnected stream, and the terminology, as I said, is unfortunate. If you have what's often referred to as a clogging layer, but the stream bed permeability needs to be less than the permeability of the underlying aquifer material.
So you would have low flow.
So it's low flow. It's still well, whether it's low or not is a relative thing. But
as long as you have a stream head, infiltrating into the sediments.
It's still infiltrating.
Right.
It's still.
So you would have to have I don't
You have a vadose zone because the permeability of the streambed sediments is lower than the permeability underneath that. It's essentially the same as a perched aquifer. Right. It's a I'd prefer to call them perched streams. I think then we know what we mean. Yes. Yeah. Okay. But the literature for 40 years has been calling them something else. Yeah. But there's been some nice work recently by Philip Brunner, who's done the maths and the physics behind these.
You mentioned complications from the hyporeic zone, and maybe I missed it, but I didn't really hear you elaborate on how you try to account for the exchanges that are going on in the hyporeic zone.
Yeah, I mean, the complications are particularly with instruments such as Seepage Meters that would record the movement in and out of the hyporeic zone, as well as the small net flux. And there are issues with when people are using temperature to measure the stream, that water moving in and out of the hyporeic zone will also change the temperature signal. So each of these methods, I think there are complications. We usually model these techniques as if it's just a one-way process. In the case of the water chemistry, for conservative traces such as chloride, there is no effect. Water moving in and out of the sediments does not change the chloride concentration or electrical conductivity. There is an issue for radon. That water that moves in and out of the sediments can pick up a small amount of radon. So we specifically calculate that. We measure the production rate of radon in the hyporeic zone. We've done some work that I didn't describe looking at hyporeic zone residence times by measuring radon within the sediments. Essentially the radon concentration within the sediments can tell you the residence time of water within the sediments. So we've tried to correct it. But it's an issue with all of these methods, and the temperature particularly, it's been modelled as one directional flow. And if there's hyporeic exchange, the upper layers aren't like that, so it is a complication.
In your radon assumptions, are you assuming that radon is just constant through the length of the stream, the source of radon?
One of those examples we had it varying as we look at the geology maps and had it varying as the geology varies. But generally we have assumed that the groundwater concentration of radon is constant. When we did an error analysis though, we measured a concentration in about 30 bores, looked at the distribution and defined our errors based on that variability. So we put an error bar that's in accordance with how much it varies in the bores. And often where we've looked at the variation in radon concentration of the stream, it's actually less variable than a lot of the other water chemistry. Essentially, it's a function of the uranium content, the radon content.
Your chemical analyses, the radon, the chloride, and the EC, are sensitive to inflow, but are fairly insensitive to outflow. So in your model, where you started with flow and then made your model more accurate as it went along, is there a difference in accuracy that you're achieving measuring inflow versus, or estimating inflow versus estimating outflow?
There is. It's a good point. There is. The traces themselves are only sensitive to inflow, not outflow. Only because we also measure flow rate, we can constrain both. And it actually happens. We've looked at error bars for outflow. We don't estimate outflow as well, but as we add the traces, the outflow error bars decrease because the flow data is the flow data and we're getting the inflow rate better. So we do get the outflow rate better. Not as well as we get, and we've done that. I didn't put them, but yeah. But we can get both terms, the inflow and outflow.
More questions? Yeah.
I should say that we can only get, we can't get inflow and outflow within between two samples. If there's inflow and outflow, we only get the net.
I know there's been a fair amount of work on trying to stabilise the ecology of rivers in Australia, where you've actually looked at minimum stream flows versus pulse flows. And I was wondering if you'd looked at any of those rivers in the course of your experiments.
We haven't, and I mean, I think there's there's a potential to look at some of these exchange processes and how they change as we manage the streams. That's not something that I've worked on at all. I know there's been a little bit of work looking at how hyporheic exchange varies due to stream management, but it's not an area that I'm really familiar with, no.
You showed how radon adds a lot of spatial resolution to your in and outflow estimates, but doesn't have any temporal resolution. It's a 1 point or it's a 1 moment measurement. Could you elaborate on that? How you go from there to yearly average?
It is. It's a point in time, and I think probably, and we've started doing repeat measurements, but that only gives you repeat points in time, right? I think probably the best way to go is to, if you're going to have a groundwater model of the area, you try to use the groundwater model. So we have calibration targets that would be inflow and outflow rates at certain times, and they could be calibration targets to the groundwater model. That gives you your extrapolation between those times. To use the traces for temporally is harder. We've done that before. We've sampled every week. You still miss the important stuff that happens less than every week, right? You would actually need something that could log remotely, which limits you to EC, really. So I think if we get several points in time and perhaps use other methods, maybe the groundwater model. But you're right, it's a point in time. It's not a point in space, but it's a point in time. Yeah.
Expanding on that question, can you take what you've done and sort of couple it to something you can measure remotely, like temperature, and say you can ground truth the inflow outflow that you might be able to get from temperature using these methods, and then use it as ground truth, because temperature you can measure infinitely in time and space nearly.
That's a really good point, and I haven't thought about it specifically with temperature. And I put up the temperature work that Steve Lowhide had done. I mean, yeah, we can. I was thinking we're using the groundwater model, and so we're essentially using the ball hydrographs to get the temporal. That's a good point that I hadn't thought about. You could use the temperature. I think there's a lot of errors in that temperature thermal balance that haven't been quantified, but doing something like what you say could potentially really help that. So that's a really good thought. But I do think we need to look at other ways to get the temporal picture. But yeah, that's a good thought with temperature that we could do by space and do continuously. Might help with that, yeah.
Okay, yeah.
I don't think I need the microphone. One more question. When you showed the picture of the seepage meter and how it measures the flux between the groundwater and the stream, it seems to me that just having the canister of the seepage meter on the stream bed would affect the flux. Is there some way you correct for that?
People have tried a lot of things to measure. Yeah, perfectly true. People have tried to make sure the bag isn't just sitting there, because the velocity through the bag, not through the bag, but the bag sitting in flowing water creates pressure effects that affect the flow. There's a lot of issues with seepage meters that people are grappling with. My stance, I think for this sort of large-scale stuff, it's not a helpful technique. It's just too local. And as you say, you've disturbed the system by putting it on the stream bed. And some work on stream bed permeability. It's incredibly variable. I mean, I've tried to use seepage meters and without success. They're not straightforward. They're sort of intuitively, it's a nice simple method, but the practicalities are really tough with them. And the people that are really pushing them now are the oceanographers to do submarine groundwater discharge. But still, the tide wave processes would have an effect. Yeah, I know it's an issue.
Any more questions? Peter, I have one question. I noticed in your model, you didn't consider the dispersion in the river, I mean the surface water. Is that important or not in your case?
Yeah, no, we didn't. We left it out partly because it makes the maths much easier if you don't bother. But no, it's unimportant, the dispersion, because we don't have sharp concentration fronts. We're sampling downstream maybe every kilometre, and so on the scale that we're working, the dispersion is really not important. We are making an assumption that when we take a concentration, that the stream is perfectly mixed across when we do that, and that's a reasonably good assumption in the streams we work at, the scales we work at. If you've got a concentration moving into a stream here and you're measuring the concentration over 50 metres downstream, you've got to worry about dispersion. At this scale, it's not an issue when we've looked at it.
Just because the distribution is very small, so actually dispersion term is very small in your case.
Yeah.
Okay, with that, let's give you a final round of Peter for his nice presentation. Thank you for your coming. So.
I just wanted to talk to you about something that occurred to me. I don't know if it's really relevant or not, but early in my career, I used to do stream sediment sampling for mineral exploration.
Yeah.
And basically what we were trying to do is characterize an entire upgradient tributary system for mineral content. Yeah. And I'm wondering if there could be some transference in thinking about measuring something that's not in the water itself, but that's representative of the water to achieve these goals. I mean, it's not immediately obvious, but just thought I'd mention it to kind of introduce the thought process. And maybe if you could, some way, is there something in sediments absorbed onto the sediments that could help quantify these processes?
Don't know. But it's something intuitively nice in that what you measure here tells you about the whole catchment. Right, that's intuitively nice.
Right. Now your objective is somewhat different. There's a lot different.
Yeah, but still, okay.
Fairly worth thinking about.
Yeah.
Well, is it possible to get a copy of your PowerPoint?
Yeah, sure.
So
I can give me a card and I can,
So, because I forget half of the things. Pardon?
Thank you. All right.
My name's John Hulls. I work with Gary Anderson. What we've been looking at is microbial ecology, which is, and I'll be very blunt, my interest is about money. We had a marvelous project to do are you familiar with the Russian River watershed? It's a river that looks very much like the one in your picture. It flows from vineyards and agriculture and such like that. And we're looking at 56,000 taxa of bacteria. We've got this thing working really well for source tracking, where agriculture comes in and such like that. And where the money comes in is the state cut all of our funding for this. It was a state water resources thing. So I called USAID and they said, if you can get some international cooperation, this fits very nicely with what we're doing. So.
Well, I think, to me, one thing that we're not doing very well, there's a lot of potential, is to link the where the groundwater is coming in with what the ecology there is. And you've got constant temperature, you've got changes in quality, so I think there's potential for exploring that further.
Well, for instance, on the program we just finished up for state water resources, we were able to detect significant changes in microbial ecology from very small inputs from Streamflow. And so it just, if I could get your card, I could.
I don't have it here. No, I don't have it here.
I've got your address off the website.
Yeah.
So I'll drop you a line about that because the river is also very interesting because of the earthquake faulting and the number of different types of terrain that it goes through. We might look out some.
You got a card?
Not with
no, similarly, yeah. I'll just go back to my room and grab mine. There's somewhere.